A skyline isn't just born by accident, it is forged. It is designed, it is calculated, it is excavated, and it is erected by machines that defy the natural laws of physics. Modern civilization rests on the shoulders of giants. Not mythical creatures, but mechanical ones. Across the United States, from the bedrock of Manhattan to the deep waters of the Gulf Coast, a silent war is being waged against gravity and geology. This isn't about simple construction. This is about extreme industrial engineering. It involves machinery so massive it has to be assembled on site, and forces so powerful they can reshape the Earth itself. Today we are looking at the titans that build America. We will examine the physics of the lift, the hydraulics of the dig, and the sheer, raw power required to turn a blueprint into a monument. This is the story of mega construction. Every mega project begins not in the sky, but in the dirt. And when that project requires going through a mountain or under a city, you don't use a shovel. You use a tunnel boring machine, or TBM. In the world of American infrastructure, these are the apex predators of the underground. Let's talk about the teeth of this beast. The cutter head. On a project like the Alaskan Way Viaduct replacement in Seattle, the machine known as Bertha wasn't just drilling. It was chewing through glacial till. The cutter head is a rotating disc, often exceeding 50 feet in diameter, studded with tungsten carbide discs. It's not about winning a drag race. It's about pure, unstoppable torque. The machine pushes against the tunnel face with thousands of tons of thrust. As the head rotates, the rock creates fractures. It chips, it crumbles. But creating the hole is only half the battle. If you just drilled a hole under a city, the weight of the skyscrapers above would collapse it instantly. That is why a modern TBM is a mobile factory. As the machine moves forward, it installs the tunnel lining immediately behind it. Precast concrete segments, weighing tens of thousands of pounds each, are lifted by vacuum systems and slotted into place with millimeter precision. This is done while the machine is still moving. The engineering challenge here is hydrostatic pressure. Deep underground, water wants to crush the machine and flood the tunnel. The TBM must maintain a pressurized face, essentially turning the front of the machine into a submarine to keep the earth and water at bay while it works. A single seal failure, a single miscalculation in pressure balancing, and the ground above could sink. This incredible power is what allows a 5-story tall machine to swim through solid rock. Once the foundation is set, the direction changes. We go up, but how do you lift steel beams weighing as much as a locomotive to a height of 1,500 feet? You need a crane that builds itself. In the canyon-like streets of New York or Chicago, there is no room for a massive footprint. The answer is the climbing crane. This is a marvel of hydraulics. The crane sits on a steel collar wrapped around the building's core. When it's time to grow, the crane uses massive hydraulic rams to push itself upward, inch by inch, lifting its entire weight off the structure. It then locks into a new, higher collar. It effectively climbs the ladder that it is building. But at these heights, the enemy is no longer just gravity. It is the wind. Super tall towers like those on Billionaire's Row act like giant sails. At 1,000 feet, the wind doesn't just blow. It exerts millions of pounds of force. If the building is too rigid, it snaps. If it's too flexible, the occupants get seasick. To counter this, engineers install a tuned mass damper. This is the heart of the building's stability. It is often a solid block of steel or concrete weighing up to 800 tons, suspended by cables or sitting on hydraulic pistons. When the wind pushes the building right, inertia keeps the heavy damper to the left. It lags behind. This movement counteracts the sway of the building. It drains the energy from the wind. It is a static, unmoving mountain of steel, waiting for the storm to wake it up. Without this passive machine, the structure simply could not exist. These are the hidden giants, the silent systems that allow us to conquer the impossible. Thank you for watching. If you found this fascinating, hit the like button and subscribe for more deep dives into the world of engineering. We've looked at the machines that build tunnels and towers. Now let's look at the machine that is changing how American manufacturing itself works. For decades, building a vehicle meant welding hundreds of small stamped parts together. It was slow, and it introduced points of failure. A single flawed weld could compromise structural integrity. Enter the gigapress. This is not just a press. It is a house-sized instrument of brute force. These machines, operating in facilities like those in Texas, exert over 6,000 to 9,000 tons of clamping force. To put that in perspective, that's the weight of the Eiffel Tower pressing down on a single mold. The process involves shooting molten aluminum into a die at high velocity. The metal must fill the complex mold in milliseconds before it solidifies. This isn't just stamping metal. This is liquid alchemy. What emerges from the machine is not a collection of parts. It is a single, unified casting. The entire rear underbody of a car, which used to be 70 different pieces, is now one. Why does this matter? Stiffness. By eliminating the welds and fasteners, the chassis becomes incredibly rigid. In the modern era, a machine's structural integrity is just as important as its engine. This single casting allows for better crash safety and tighter manufacturing tolerances. But the engineering required to build the press itself is the real story. The steel plates that hold the mold must remain perfectly parallel under 9,000 tons of force. If they deflect by even a fraction of a millimeter, the part is ruined and molten aluminum flashes out like a grenade. Precision here is measured in microns, but the forces are measured in kilotons. Finally, we move to the most hostile environment of all, the ocean. Here, construction doesn't happen on the ground. It happens on water that is constantly trying to destroy what you are building. Consider the heavy lift vessels operating in the Gulf of Mexico. These are ships designed for one single purpose: to lift entire factories and place them onto legs in the middle of the sea. When lifting a 10,000-ton module, you cannot use anchors. They are too slow and not precise enough. Instead, these ships use dynamic positioning. A computer reads the wind, the waves, and the current, and automatically fires multi-directional thrusters to keep the ship in the exact same spot within a few inches. It is a digital battle against the elements. If the computer fails, the load swings and the disaster is catastrophic. And what supports these structures? In deep water, you cannot build a tower to the bottom. Instead, we see the tension leg platform. These massive cities float, but they are pulled down by steel tendons anchored to the sea floor. The buoyancy of the hull wants to float up. The tendons pull it down. This tension makes the platform as stable as if it were sitting on concrete. It eliminates the bobbing motion of the waves. It essentially tricks the physics of the ocean. Every single plate of this armor is precision cut to withstand hurricanes, salt corrosion, and the relentless fatigue of the sea. Failure is not just allowed here, it's expected. Because failure in testing is infinitely better than failure in a hurricane with a crew on board. From the darkness of the tunnel to the height of the skyscraper. From the heat of the foundry to the crush of the deep sea. Modern engineering is far more than just pouring concrete or welding steel. It is a symphony of extreme forces managed by extreme machines. It is the application of intelligence to overcome the brute resistance of the physical world. What emerges from these sites is not just a bridge, a tunnel, or a tower. It is proof that with enough torque, enough pressure, and enough precision, we can reshape the world around us. And that is how the modern world is built. Thanks for watching, and if you found this interesting, don't forget to like and subscribe for more deep dives into the world of technology and engineering. See you next time.